So thank you for all the attendance to be here, share this couple of hours in this workshop, and also I would like to introduce the second session about oneAPI, this new paradigm of programming, of parallel programming in heterogeneous computing. For me, it's a pleasure to be here with all of you. And I'm going to continue in this second session to introducing some advanced concepts related with the DPC++, the data parallel C++. And also I would like to show you some demos and at the end of each part. So I divide the second session of today in two main blocks again. The first block corresponds with the data parallel C++, what I title advanced here. And basically, I'm going to summary some of the concepts that we were working the last day. And also we are going to deep in some concepts related with some of the concepts related with oneAPI, which are relatively new, respect its standard SYCL. So the DPC++, it is based on SYCL, but however, Intel have introduced some particularities which made a bit stronger and a bit you can express the parallelism and also improve your application a little bit more respect the SYCL standard with special add-ons such as subgroups that I will introduce later. You can manage the data with shared memory, unified shared memory, which is some novelties in respect with SYCL. So this aspect will be trying to show today, and also some aspects related with the standard SYCL. So it will correspond with the first block, and I will finalize this block with some demos about I will try to connect to the Dev Cloud, Intel Dev Cloud, and show you some examples about DPC++, the first Hello World code, some aspect related with the subgroups and unified shared memory. And in the second block, I'm going to move on some performance tools, high performance tools, in order to check what are the main bottlenecks of our code, what are the inefficiencies, and how far we are of the limits, the hardware limits of our application developed. So let's move to the first block. This will be the agenda. So the first part will be corresponds with a briefly summary of what we'll introduce about DPCC concepts in the last day. So we are going again to show you how you can create an heterogeneous code in one file, a unique file, which is one of the purpose of SYCL, to develop your own code for the host and the device in the same file, and you can compile with the same tool, with the same compiler. In fact, we are going to deep in how you can select different devices. If you remember from the last day, one of the strengths of oneAPI is that you can develop your own code and try to export this application to different devices, as the CPU, the GPU that it is here, the special hardware for artificial intelligence, or even the FPGA. So in this point, we are going to show how you can select a specific hardware. And also, we are going to move on how you can manage your data between the accelerator and the host. There are basically buffers which came from the standard, the SYCL standards. And also Intel have added some improvements related with the own hardware, which is called unified shared memory, in order to avoid the inefficiencies in sending and taking back the data from the accelerator. Later, I'm going to present how you can execute your code and how you can express the parallelism between different kernel. And in fact, maybe the kernel developed, there are some data dependency between all of them, and how the schedule can planify the execution of all these kernel. At the end of this main block, we are going also to present some subgroups, which is a concept that Intel have created. I will show you how you can express the parallelisms in terms of ND range, which is the most common way of express parallelism by means of subgroups and work items. However, Intel have added another hierarchical abstraction of parallelism level, which is known as subgroups. So I will present later on also what are the main feature of these subgroups in order to exploit hardware, special hardware of Intel, such as GPUs. So this is more or less our agenda. What we are going to work today in the first main block, and also I'm going to finalize with some demos, some code that we can run in the Intel Dev Cloud cluster, and all these demos correspond with one of each item of the agenda. Well, so the main objective, the main target of today is to introduce the data parallel C++, which is one of the core, the heart of the oneAPI toolkit. And this data parallel C++ involve one language which is based on C++, so it is based on a standard. The C++ have a really long roadmap since 30-40 years. So it's a new layer that can be seen over the C++. So your code could be compatible. Your code developed in C++ is totally compatible with data parallel C++. And what I'm going to show you in these slides and today is how you can structure your code, your own code, in order to offload some of the code to an accelerator or a device, and also some key concepts related of buffers, of the queue, and another concepts with data parallel expression that you have to take into account in order to improve your code and speed up the tasks of writing the code. So this is more or less what we are going to talk today, and our main target. Well, if you don't attend to the last session, I'm going to summarize here what are the main challenges nowadays related with the hardware and related with the point of view of developing code in different and heterogeneous platform. So nowadays, that is true that you have your own computer that you have bought maybe last year, 2 years ago, and inside of your computer, on your computer, there are many things that maybe you don't take into account. For example, of course, everybody knows that you have one processor, one general purpose processor, which is known as CPU. Basically, is the heart of your computer, where all the work is executed in the CPU. However, there are another type of devices that also is inside, and this type of devices is focused in creating an heterogeneous platform, which is one of the ways that nowadays have been shown related in all the computers. So actually, we have normally one general purpose processor, and actually in the same chip even some specialized hardware as GPU. Normally, it is done because all the workload that you have in your own computer, there are different parts who are running better in one of the devices to respect to the other, and there are more and more and more specialized hardware in your own computer. It is not only in your own computer, maybe in your mobile, your smartphone that is in your pocket. You don't take into account that you have also multi-core, and maybe your core run a different frequency. There are big cores and little cores, and also there are GPUs and this DSP, digital signal processing, and another type of devices. And one of these things comes because actually we have a specialist workload, and this workload runs better in one of the devices respect to the other. When I say it runs better, I can focus that maybe it runs faster. This is one of the points, but maybe it runs with less power footprint. So the power consumption is one of the keys that we have to take into account nowadays. And even more if you have a smartphone and the life battery are in a strange relationship with the consumption of each device. So this specialized workload and how this specialized workload have to be run in different type of devices, this is one of the main challenges that we have actually. Because if we are focusing that actually most of our workload it is based on the data-centric, we will need specialized hardware. And one of the main challenges is how we can develop an application and can be run in different type of the hardware with a relatively low programming effort. This is main of the key, because actually we don't have any language, any API that can be executed in what we can develop a code that can be run in each of these devices. So the main of the problem came that there are no tools. There is an inconsistent tool across most of these platforms. So, of course, from the point of view of developing effort, each developer have to think about of each of the hardware, each of the devices, and how can express in the best way these porting elements. So this is This is one of the most important things. This is the most of the challenge that we have nowadays respect of the architecture, that we have different type of architecture, we have different type of problems, from scalar problems, vector problems, or another type of problems, how we can map all these problems in all the specialized hardware that we have nowadays. Well, so this is the main challenge that trying to reduce this gap, oneAPI. Sorry, one moment. Well, so this is one of the main things that we have today. So from the point of view of oneAPI, I would like to notice you that oneAPI came from Intel. However, it is an industry initiative. And another of the talent that we have actually is that related with heterogeneous computing in the last few years with the eruption of NVIDIA and its GPUs and so on. One of the problems that we have is we develop a code, for example, for this type of hardware such as GPUs, but it is not possible to reduce much of our developing code in another architecture because the programming model are linked to the vendor. So what another strength we try to cover oneAPI is to be an alternative of a single vendor solution. So we can write down each code and can be running in different type of devices, and in all the vendors could adopt this solution. So this is another strength that we would like to focus. It's not only to porting your code to different type of devices, but also you can use your code in different type of vendors, which is really, really interesting. So oneAPI each core, the heart of oneAPI, it is the Hpc which is known as the data parallel C++ compiler, and there is also a language you can express all the parallelism in terms of data parallel C++. I would like to mention that another strength of oneAPI and the data parallel C++ is that it is based on a standard which is really important in order to migrate your application to another hardware, another vendor. So C++ is actually support with all the vendors. And another thing that I would like to notice is it is not only based on C++. There is another layer over the C++ that is SYCL. SYCL, it is focused on heterogeneous computers, so you can express some of this parallelism using different type of devices on C++. And DP C++ is C++ plus SYCL plus extra an extra concept that I would like to show you today. So this concept, if we mix all these concepts, we will have finally one powerful API that you can design your code not only for CPU, but also for GPUs, FPGAs, and other accelerator that will come in the future. All this processor, in terms of oneAPI, is what it is called this cross processor, or the cross, how you can cross your code to the different type of processor units. So this is another of the key of the strength of oneAPI. However, it is not only focused in the portability, it is also focused on trying to express and obtain the best performance on the hardware. So you can also use a low-level hardware interface in order to improve your application. Our experience said that if you are using data parallel C++ against another solution in a low level, maybe the overhead that you have to pay only will be 5% or 10% slower than the low level. So I think it is not a big gap that you have to pay. So the portability, this is one of the strengths, and you only have to pay a little bit of using your application in a low level. So this is another thing. As I told you before, there is one of the strengths is that came one layer over C++ and another layer from SYCL. I would like to mention also that is another strength related that all these solutions, oneAPI, the data parallel C++, came from these open standards, the open standards that are C++ and also SYCL. And it have two opportunities. The first one corresponds that all the community can improve and promote these open standards, so can create some solution based on this open standard. Can also improve some of the parts and also extend some of the concept and consider necessary in different type of new hardware and so on. And the other is that it is totally open. You can easily adopt in your hardware. So it is not only used for Intel products, but also you can use in another ones, for example, in GPUs, in CUDA or another one. So you can reduce your code, you can reduce your solutions across different architecture, not only focus in Intel, but also in another's backdoor. This is the other strength that I would like to show you. So from the point of view of oneAPI, there are two concepts that I would like to show you here. The first one corresponds that you can apply for direct programming by means of the data parallel C++, or you can reduce another optimized libraries which are developed to use, for example, CPU, GPU, or another type of devices. So there is direct programming if you have to port your code, or I will show you later how you can reuse your code. But if you have to create a new solution by zero, you can came from this data parallel C++ direct programming. And also there is another type of programming based on libraries. So you can reuse these libraries and invoke the function of these libraries, and it is transparent to you how you can use the different type of devices. So this is two ways in order to use the oneAPI. Well, so as I said before, data parallel C++ is the heart of oneAPI. So in these new slides, about what are the basic of data parallel C++. Well, so it's more or less the summary as we were talking the last day. So first of all, normally when you create a code and you would like to use oneAPI, the first thing that you have to add is this include, which corresponds with the SYCL headers. And actually, you normally insert this new line. We say that you extend the next space of SYCL in order to reduce the data, the source code of your application, because this SYCL you are using all the space of the SYCL particularity. Well, so first you have include your headers and you have include and extend the namespace of SYCL. You can create the first code as we were seeing last day. For example, in this main, we create three arrays, the A, B, and C. And now we are preparing the code in order to use the heterogeneous computing. So the first thing is to create some special data management that are called buffers. We will see later in more detail what are the syntax and how you can use it and now. But you create these buffers in order to link the data that you have previously initialized in the host and can be used directly from the device or even the host. So these data managements are done by these buffers. So in this buffer, we are attached to the A that is here, and it is attached by means of this variable by A. Also, there is a lambda that corresponds, which are the dimension of this buffer. That of course corresponds that this is a buffer and array of one dimension only, so it is here one, and the dimension corresponds to 1024 elements. Exactly the same for the buff B and the buff C. So as I told you here, we are creating a buffers, and these buffers are linked directly with the information that was created in the host. Well, the second point corresponds of defining what are the scope of this scenario. So with this key, we say that in this part will be the creation of a queue, buffers, and another type of concepts in order to execute the code in a heterogeneous computing. So with this part, we are saying that the buffers, the buffer's life are coming only being during this part of the code. So the creation, it is done here, but when it's finalized, this section, all the buffers are destroyed. So this is the second concept that I would like to show you here. Well, after that, we are creating a queue. Where we are creating the queue, it is easily to define the queue. It's only like this. It is define a default queue. We will talk about the queues later on how with this queue we can select the devices, but in this case we are using a default queue. Well, the queue is another mechanism in order to add the code that will be executing the device, the data that will be allocated maybe in the device, or what data have to move from the host to the device and coming back, and also what are the mechanisms to synchronization between the host, the device, and even in the devices. So we create a queue, and in the queue we are going to submit all the work that are executing in the device. Well, after creating the queue, we should meet the code that we are going to execute in the device. So here in this submission, we are saying to the device that there are some part of the work that are submitted to the queue that have to be executed in the device as a kernel that is right down here. So here it corresponds with the lines of the kernel that we are going to see later. So the mechanisms in order to create all the work that have been submitted to the devices and how can be synchronized, how the data are going there and so on, is called the queue. Later, when the queue are created and the work are submitted, we are creating another special variables here that are called accessors. Accessors are really important in order to access to the data, the mechanisms that are previously defined in the buffer. So here the accessor said that we can use the buffers to access to the data. In this case, the buffer A, it is access in a read mode. So here it is said that it's written in a read mode. Here is the handle in order to express that all the work that is submitted here is in the same region. In the same way, it is access to the def B by means of this variable that is B, and take into account that there is an auto here, so it is not necessary in times of compiling. The compiler decide what are the typing of this variable. Of course, in this case will be float because the buffers are allocating data for float, and the link of this float corresponds with the data A, for example, that is also float. But with this auto in compiling phase, it is determined the data of the data type of B. Well, as I noticed before, A variable, it is in a reading way, the B variable is in a reading way also, and the C variable is only to write. Because in this case, we are using the kernel that is in fact here, and it is adding the vector A plus the vector B, and it is stored in the vector C. So the accessors are really interested in order to link the data that will be corresponds to the kernel to the buffers. So this is another mechanism in order to access to the data that can be come from the host. Well, finally, it is expressed the kernel. So the kernel, as I mentioned, it is right down here. It only will be executed in the device. And this kernel, it is said that the parallelism is expressed by means of this function. That is a parallel for, so the for creates 1024 identifiers, and each identifier that is here in one of the dimensions, it is one, that is in one of the dimension of this I, its thread are executing this instance, and this instance which will be executed directly in the accelerator. And finally, when this work finalized, the buffer are destroyed, the data C that are allocated by means of this buffer are the data are allocated here that will correspond with the C, and finally in the host code that is here, it is on the content of C. So what I would like to notice here is in all these lines, with a few lines, you can express the code that have been run in Accelerator by means of this kernel and this construction of this parallel for. And with the construction of a queue, you can send to the accelerator which are the lines of the code and also which are the data where the kernel is executing respect to this data. Well, how you can select the device exactly? So coming back from the sample that I mentioned before, the kernel was done here, and it is passed a lambda function. A lambda function that, for example, here it is said that the range of this function will be 1024. So we are going to create in 1024 instance of this kernel, and in this kernel here with this lambda, it is said that this variable corresponds with the identifier of each of the iteration. Well, but one of the things is where it is execute code, and as I told you before, in this queue it is not done as selections, as explicit selection. So the runtime of data parallel C++ of DP C++ decides where this kernel is exactly launched. Well, in SYCL 1.21 require the name of the lambda. There is another of the things that Intel have improved respect of the SYCL standard. In the SYCL, it is necessary to include here the name of the function of the kernel. The rest of the lambdas is exactly the same. So this is only what I would like to notice. And finally, in the kernel, as I told you before, in this lambda, it is specified the range of the number of instances that is created with this lambda. Well, is 1024. Well, and each instance corresponds with one of the iterations in one of the dimensions which have an identifier different with this I. Well, so the final kernel, as I mentioned, corresponds only to this line, this block line that will be executed here in the device, and it is expressed the parallelism by means of the parallel for. So there are different ways in order to construct the execution in the device that it is shown here in the next slide. So the first one corresponds with a single task. Well, the single task, as its name suggests, only one kernel, the kernel is executed, but in a single work item. So only it is created in a single work item. And in this work item, it is executed as in sequential. Well, normally this single task, it is very useful in case of your device is the SPGA. In the SPGA, normally it is used as a single task because inside of a single task it is expressed the parallelism, for example, in terms of unrolling, in terms of byline parallelism, and so on. So normally the single task it is used, as I told you, here in the SPGA. There are another way in order to express the data parallelism, the classic data parallelism that will be here with the parallel for. The parallel for, in this case, the range can be expressed in 3 dimensions. So you can express using this 3 dimension the number of instances that are going to create in this 3 dimension. So it will be 1024 cube instance. Also, you can express by means of empty range that are going to present later, not only the empty range, but also another hierarchy level of parallelism by means of work groups. Will be a work group of 16 cube elements. And also, you can express the parallelism by means of a hierarchical parallelism that is done here. You can express parallelism hierarchically by means of work groups. In this case, you are using work groups of 1024, and inside a work group, you express what will be the number of work items in this case. So there is two levels of parallelism. There's parallelism use of work groups, and inside a work group, what are the number of instances that are going to create it. Well, so how you can select a device? How you can select a device? Well, you are going to select a device when you create a queue. So as I told you before, when you create a queue, before was by default, but in this case, you select the device by means of this selector. In this selector, you are selecting a special device. In the case of SYCL and oneAPI, there is a special class related with the selector that can be defined as it is shown in these lines, in these code lines. So when you create a queue and you select a selector, this function decides which of the devices are selected are selector in which device are running your kernel. So as can be seen here, for example, first of all, it is check if your device is a GPU, and if it is a GPU and the vendor came from Intel, it is given a rate that is 3. If it is not came from this branch, check if it is a GPU and it's given a rating of 2. And it's not a GPU. Finally, it selects the CPU with a rate of 1. So with this selector and the class we have created here, from the point of view of the hierarchical point of view, decide that first of all, if there is an Intel GPU, please check it. So prioritize the Intel GPU. If not, check if there is another type of GPU and select it. And finally, if there are no GPUs, select the CPU. So you can select the device as you prefer by means of a custom selector. If not, you can use another selection. When you created the queue, you can select the CPU, GPU, or another type of selection. So more or less, this is what is done here. Okay. What I would like to notice is the execution of the kernels are done in a synchronous way. So from the point of view of SYCL, your application will have two parts, the host code, where you are going to express what lines of the code have to be creating and executing in the host. And also when you decide to create the queue and inside the queue insert the kernel, it is created a special graph with the dependencies between all the kernels. So the execution will be totally asynchronous when it is create a queue. The queue it is running in another thread respect to the host, and it is executed independently. And in this queue, it is executing the kernels or in order or out of order, depending how you can express the queue. And the synchronization between the host and the queue can be done by means of synchronization operation that are going to present later. But what is really important is that it is created a graph of dependencies between all the kernels, and the runtime of the SYCL decide what are the order of the execution of this kernel. And as I noticed, from the point of view of the host, it is launched the queue and the execution of the queue, and it is done in a synchronous way from the point of view of the host. And all the execution of the queue are managed by the runtime of SYCL. So coming back more or less from the example that I presented before, in this case, it is create the buffer. The buffer, remember that is the way that you can manage the data that are transferred to the kernel in or out way. Later, it is submit in a queue. In this case, also it is create a default queue, and all these parts are executed in the host, as it is mentioned here, and only the lines corresponding with the kernel that it is done here, exactly offloading to the device and executing in a previous device. So all these kernels that possibly are executing in the device are creating in this graph, in the graph of dependencies. The runtime decides what are the order or execution of the kernel depending on the dependencies that are required between all the kernels. So in this example, for example, we are creating different kernels, the kernels 1, the kernels 2, the kernel 3, the kernel 4. So there are 4 kernels at this example. However, the first kernel that is defined here, it is submitted, this kernel, at what is done by means of the accessor. It's this variable, the variable A, it accesses in a right way. Well, so the buffer that was defined here, we are going to write the data in this buffer by means of the accessor. It corresponds with the kernel 1. In the kernel 2, also, it is accesses to the same buffer, the buffer A, and also it is done in a right way. So it is necessary to execute the kernel 1 and the kernel 2 in a dependent way, because there are data dependencies between the writing of the buffer A and the buffer A here. So it is necessary to execute the kernel 1 first and the kernel 2 later. In the case of kernel 3, the buffer which is accessed is the buffer B. The buffer B also is accessed in a right way, but can be executed at the same time of both of these kernel previous, because there are no dependencies between the data. Kernel 1, kernel 2 only are accesses to the buffer E, and kernel 3 is only accesses to the buffer B. So buffers are different, so these kernels can be run independently. They are totally parallel. And finally, the kernel 4. The kernel 4 are accesses in buffer E and buffer B. In the case of buffer E, it is read. So it is necessary to execute previously kernel 1 and kernel 2 because they have to write the data to the buffer E. And in the case of buffer B, it is read and write. So we have to wait until the kernel 3 it is finalized in order to proceed the kernel 4. So when you submit all these kernels to the queue, it is create a graph that as it is seen here in order to express the dependency between the data that corresponds with all the kernels. So as can be seen in the graph, the kernel 1, kernel 2 necessary to be kernel 2 wait until kernel 1 finalize. Kernel 3 can run in parallel with kernel 1 and kernel 2 because it's accessing to the buffer B. And when kernel 4, it only can be launched when kernel 2 it is finalized and kernel 3 it is finalized due to the dependency of buffer, the accessing of the buffer A and buffer B. So this is what I was saying here when I say that it is created the graph that executes asynchronously the host program. So when it is created, the queue submit, again, the host is continuing the execution until it finalizes. And in another way, the kernel can, or all the kernels can be executed at the same time as the kernels. Well, so in this part, I'm going to present more or less these ideas of what are the structure of the code by means of some of the essential examples that can be run by the Intel Dev Cloud. The other day I present how you can create a classical hello world. In this second part that I mentioned the previous day, I'm going to present how all these ideas of data parallel C++ can be used. These concepts can be used in a program. So as I comment the last day, you can launch the Jupyter Notebook in the Intel Dev Cloud, and okay, we are going to launch the Jupyter. Let's see if this works better than the last day. Even you can not only launch the Jupyter, you can check all the samples of the Jupyter Notebook that I was commented during these sessions. Here you can click here and also go there, and also you can connect directly to the Dev Cloud by means of a cell of SSH. If you are using Windows or MacOS or Linux, you can configure all of them to connect to the Dev Cloud by means of a cell. Well, let's see if the Jupyter is ready. Yeah, it is ready now. So if you check here in the second module, the Jupyter Notebook in theory will be open. Let's close the other one. Do not interfere what I'm doing today. Well, so in this part, what is presented is how you can select a device. Well, when you create a queue, I don't know, maybe we can do this bigger. When you create a queue, you can select the selector. By default, if you say like this, was more or less all the samples that I saw you in the slides were written like this. By default, the runtime of SYCL and the oneAPI select the device with more hardware capabilities. So normally, if you have a CPU and GPU, normally it is selected the default device as GPU because normally it has more computational capabilities. But you also can select the device by yourself, checking when you define the queue. The selector can be the default of the host or CPU of the GPU. And in fact, if you later print which are the device selected, but here it said that will be, for example, CPU or the GPU and so on. So let's see the first example here. In the first example, we are creating a code to check which are the selector chosen here. So in this case, for example, we are selecting the CPU and we are printing which are the device finally selected. So in these lines, first of all, we are going to run this. So it is create the file, the source code file here. And now in this line, we are going to build and we are going to execute the code in one of the queue. So we are launching, and maybe I saw you here the last day by means of this command, the command queue. It is launched to the cluster queue, one of the jobs that the job corresponds with this run GPU .sh that execute the the code related here. So nowadays it is executing here. I don't know if I can. Okay, the job we finish with 64 corresponds with the job of run GPU. Let's see how it works. Because normally it is working so quickly, but the other day was taking a lot of time. Okay, the job finalized. So in this case, if you remember, I select the CPU. So here in theory, the device is CPU. Of course, it is CPU is the Xeon CPU. Well, we can select the GPU also. Let's run the code, write down the file again, compile, create a job, and latch the job to the queue, the run GPU job. But again, it is delayed so much. Maybe it is better to open a console and terminal and do by the terminal. See, because I don't remember exactly what it was. So it's oneAPI essentials. Well, it is corresponds with DPCC programming structure. Here it is created in theory the file in the source directory. Which was the name of the file? Okay, now it is running. GPU sample. Okay, it is running. Let's wait a bit. Okay, let's see if, okay. Now, for example, we select the GPU at this here, and now the GPU was selected. Well, so it's very easy to select each of the devices only to write down the proper selection when you are creating the queue. Well, later it is shown here that when a queue is created, you submit the command group code that corresponds in this case of the kernel, and it is expressed the parallelism by means of this parallel for. So it is created a group of queues as you remember in the last day. It is create a queue for each devices. So different queues can be attached to different to the same device, but each queue is only allocated with one of the devices. You can select the queue by default like this. You can select the queue explicitly by yourself, selecting CPU, GPU, or SPJ. In this PJ, you have to write down like that, or even another accelerator. Well, how you can express the kernel? So as I mentioned, for example, you have the code in the host in C++ like this, with the parallel for all the instance, the 1024 instance, and are executed in each instance execute only the adding of one of the elements. And you can access to the data related with the ID of the element and what are the range of the elements. So in this case, for example, the ID will be one number between 0 and 1023, and the range will be 1024. That's okay. Well, let's continue with the slides. Let's continue with the slides. Well, how you can manage the data. As I told you, normally when you have a host that can be seen here as CPU and different type of devices, normally the memory are different between the host and the devices. So the memory model say that the memory of the devices are completely independent with respect to the point of the CPU. There are separate memories. So if you would like to launch a kernel and the kernel in the queue needs the data necessarily have to be transferred to the device. Previously, the kernel are executed, and when the kernel finalize, the data have to be come back to the host. As we are going to see in the next slides, by means of oneAPI or by means of SYCL, you can do the movement of the data in two ways. In the way of explicit, where you are saying which data have to be allocated to the device and which data have to be back to the device, or an implicit data, which means that during the runtime, it's the runtime who decides which data have to be transferred to the device in an in or in an out way. So you can do in the same ways. Well, respect to the data management, oneAPI support 3 different abstractions. Normally, the abstraction that we were talking during this workshop and the previous day is the buffers. In the buffers, you can create arrays in 1 dimension, in 2 dimension, in 3 dimension. These buffers are not cannot be accessed directly. It is accessed by means of accessors. And you have to create an accessor in the queue to access to the buffer. And you are in the host, you also have to create an accessor to access directly to the buffer. So this buffer cannot be accessed directly, have to be accessed by means of the accessors that I was mentioned before. Well, this is the first abstraction that we were talking about during this workshop and the previous workshop. There is another way that you can use it is by means of images. This is not talking about this workshop, but you can notice in the documentation of SYCL and oneAPI by means images includes special support as format images. For example, you can access not in a linear way, you can access with 2 components in a matrix or even in 3 components and so on. And there are also by means of images, you can extrapolate data between some parts of the images. And the other way that we are going to talk a little more here during today is the unified shared memory. Well, the unified shared memory is the best or the easy way to integrate your code to the C++. Because with the unified shared memory, you can access through the host and the device directly to the memory that in theory are shared between both of the devices. If we see here, for example, the memory model, as normally it is came also from CUDA and OpenCL, and normally there is a device memory which is called global memory. This memory, it is accessed from the host by means or explicit way. You can copy the data here to this memory. And normally, the compute units have each private memory, which are L1 cache or another type of memory. And also there is a local memory, which is shared memory between all the compute units. Okay, so there are different levels of the cache. Maybe there is one level which is totally private and the other are shared between the different compute units. But the only way to access from the point of view of the host is by means of global memory. And all the work groups and all the work items can access to the global memory. Well, the memory model, as I said, can be accessed from the host to this main memory by means of the buffers, and the buffers are the accessors that I defined previously in the case of buffers. And these buffers, it's a representation of the data that can access from the host and from the device, from both of them. In fact, the buffers can be allocated in the host, or normally it is allocated in the host, and all accessors are supported, such as read, write, or read and write, and also some operations are supported, for example, atomic operation, when it is inside of the kernel. So normally the best way in order to access to the memory model of SYCL is by means of buffers. However, when you have different type of buffers of the same buffer, this buffer can be accessed from different command group or for different queue by means of different accessors. So in this case, for example, you run one of the kernel in a CPU, one of the kernel to the GPU, and both of these kernel can access to the same buffer by means of its accessors, and its accessors are independent by means of the queue. The queue are totally different, so the accessors are totally different. There are different memories where you can access to the CPU or GPU. So in the case of using buffer, there are two ways, as I mentioned before. There is explicit data movement and there are implicit data movement. We are going to tell a little bit more here. So the explicit data movement, as can be seen here, it is created a queue where it's, sorry, I don't know what's happened. Well, it is created a queue when it is creating a queue. Here it is submitted one of the jobs. In fact, there are 3 jobs that are submitted. In the first job here, it is explicitly data movement. So in this case, with this main copy, it is copy the data which are allocated here in the host array, and it is copied here to the device array. Take into account that the device array is directly malloc to the device. So device array is the memory which are allocated directly in the device. So in this case, the transfer from the host to the device are done here. So this is explicit movement. In the same way, the last one, it is done exactly the same, but in the other way. So the data that are allocated in the device are copied to the host. Here in the middle is exactly the kernel which is really executed in the device. That is done in the accesses to the memory device, and only is increment one of the variables of each array. So this is explicit movement. The main of the problem of the explicit movement is more verbose code. So it is necessary to create here in order to send the data to the device, and also it is created this code in order to take the data back from the device to the host. So it's more verbose. So this is what shared memory, unified shared memory, try to solve. By means of the shared memory, you can migrate the data from the host to the device directly, instead of using this explicit allocation. So let's see a little more about this unified shared memory. So the idea is normally, as I mentioned, you have different type of devices. You have a device memory between the device and the host, like here. The space, the memory space is totally different. However, in the devices of Intel GPUs, normally it's an integrated GPU which is in the same chip. It's a system of chips really. There is a multi-core, and with a multi-core also there is a GPU inside. So both the CPU and the GPU really access to the same memory. So in theory, from the point of view of the hardware, the GPU can access to the same memory and as the CPU. So why not to create, from the point of view of the software, the idea one unified shared memory when you can access for both of the points, the CPU or GPU. This is more or less what we are using here, because in the Intel's integrated GPUs, can access to the same memory space. So this is the idea. This is more or less the idea of the unified memory. Well, let's see how it works the buffers, the access of the buffers. In this case, and later we are going to present how the unified memory it is used in order to see how you can reduce the number of the line writing of this code. So if you remember, because we have been working during this example today many times, we are creating the buffers. And the buffer are accessing by being of the accessors that are here in the queue, the queue that previously was submitted. And only the kernel corresponds with these lines. So in this case, the buffer are created. There is not explicit movement, so it's an implicit movement because the runtime decides when the data have to be allocated to the memory of the device. So before the kernel it is launched, the data A have to be copied to the memory of the device, and also the data of B. Well, so before this point, the movement of the data have to be done implicitly, and later, at this point, they have to be a copy out of C because C it's right, so the kernel write the data in C. So at this point, have to come back the data from the host, from the device to the host. Well, so this is more or less what with buffers we have previously seen. What will be done with unified shared memory? Well, first of all, I would like to show you the syntax of the shared memory. So the syntax of the shared memory are like this. So it's more or less the same way. You can create a malloc, but in this case, the malloc is specified that is shared. And in the case of using C, it is set the size of each element. In this case, you only put the size as elements. But it's important to notice that in all the definitions, the queue have to be specified. Well, and in the way of free will be like that. So it's relatively easy done. Well, how to do it? Well, let's do the same example. Okay. In the same example, here, for example, we create an array that is shared. It is initialized another array, but only in host. Okay. And when we submit the data, and we are doing this is copy the data from the array and adding and increment one position, and it is copied to the shared data. It is an explicit access because at this point it is copy all the data, and later here you can access to the host to the shared memory. The shared memory are shared on the host and is totally accessible. The only way that we have to take into account is we have to wait here in order to be sure that this kernel is finalized. So this is more or less what we are going to present. So as a summary, seekers provide the buffer memory abstraction. What is new in oneAPI is the unified shared memory. The use of buffer memory, the main of the problem that it have is very verbose sometimes, so it's an inconvenient for programmers to write down like this, and sometimes it is proven to create some errors in the developing phase. So the idea of using unified shared memory as a pointer base help us to the porting tags to accelerator, also give the programmers enough control, and are totally complementary to the buffers. This is one of the idea. Well, in fact, here I'm going to present how you can use in this data management the unified shared memory in an implicit way and also as explicit way. You can use in both of the ways as in buffers. Well, in an implicit way, as I noticed in the previous example, I was creating the buffer with this here malloc device. So it is only allocated in the device. Here again, it is copy to the device, so it is done exactly the same. It is necessary to apply for a synchronous phase in order to finish this to be accessed. So the data now are completely in the device array. So in the device array, we are again incrementing the position, and later here are copied back to the memory of the host. It is implicit because the copy in and the copy out have to be done implicitly. Well, in another way, if we are using the shared memory, we initialize the data here in the host, but when we are creating the submission of the queue, we are directly using the shared memory, and it is done like this. And directly, this data array that is shared can be accessed from the host and the device directly. This is more or less the idea of the unified shared memory. Well, so let's do a little bit more, and later we are moved to the Jupyter notebook. From the point of view of the schedule, the kernel schedule, I mentioned that when you create a queue and you send the submission of the kernels to the buffer, it is creating a graph in order to check what are the dependencies. You can also add in what are exactly the dependencies in order to see what are the order or the execution of the kernels. So in this case, for example, we are creating 3 different kernels. First kernel, second kernel, and the third kernel. In the first one, we initialize that data 1. In the second, we are initialize data 2. And finally, in the third, we are using data 2 that was created previously here. And we are writing in the data 1, but we also need the data 1 from here because there is 1 plus equal operation. So in theory, you can see the data flow and the execution will be like that because the initialization of data 1 and data 2 is totally independent of that. So can be done in parallel this phase. And when we have to add the vector, it is necessary to wait until the data 1 and data 2 are initialized in order to process the vector adding. Well, and finally, here there is the last kernel, which is a single task. So there is only one there is like only one thread here. There is only one instance here that we're doing all the reduction. So it is necessary to be completed the previous kernel in order to launch the rediff. Well, the only way to maintain like this the correct order can be done in an ordered queue. However, these potential parallel kernels cannot be done in parallel because it is the queue in order. So it is necessary to execute the first kernel in order to execute the second kernel because the queue are in order. So we are not expressing well the parallelism available between launching the kernel of initialization data 1 and data 2 and potentially can be run in parallel, cannot overlap the tasks, even there are no dependencies. So the only way to do that is with a queue out of order. With a queue out of order, we are saying that you can execute the first data initialization, you can execute the data initialization in data 2. Well, but we are saying here this kernel, we are not having any dependency to the previous one. Because this kernel, we are creating a data dependency that we are known as E1. Here we are creating the data dependency that E2. But the third kernel, the vector addition, it is necessary to finish the initialization of data 2 at data 1. So here we are seeing that there are data dependency between kernel here at the other kernel. So by this, we are saying that this kernel, the kernel corresponding with vector adding, necessarily have to wait to the previous one, as I notice here. So like this, we can create the graph with no data dependencies between all the kernels. Only there are dependencies between kernel 3 to the kernel 1 and kernel 2, and can be run potentially nowadays in parallel the initialization of data 1 and data 2. Of course, the last kernel, the kernel of the reduction, necessarily needs to be finished the previous kernel. So there are here the dependencies. So the graph will be constructed as it is noticed here in the left part of the slide. Well, it is remarked in this part. These are the dependencies. So with this, we can check what are the dependencies by means of the kernels. So let's go to the third Jupyter notebook in order to show how the unified shared memory works. And let's go to see how the kernel dependencies are expressed. Well, we're going to the third notebook here. Well, the previous overview is where I was discussing previously. Normally, we have the memory of the host at the device totally separate, but the integrated GPUs of Intel can access to the same memory. So here there is a table where it is summarized where the data are allocated exactly, and if it is accessible, if you can access from the host or the device. So if you have created a malloc device, it is allocated in the device, and it is only accessible from the point of view of the device. If you are creating a host by means of malloc host, it's accessible from the host and the device as well. And in theory, this data it's allocated only in the host. And it is shared because you are creating the data and allocating the data by means of malloc share. Can be accessed from the host, can be accessed from the device, and you can migrate the data depending on the number of accesses to this buffer. This data can be allocated implicitly in the device or implicitly in the host, both of them. Well, the syntax, as I told you, it is very easily to write down. It's malloc share, the number of elements, and also necessary to link with the queue that is executed. Well, so let's talk about this example. It is creating by means of this malloc share. It is initialized here in the host, and now it is computed with this data here in the device. So in both of from the point of view of the host and from the point of view of the device, you can access to this data. So let's do it. Let's click on the run. It is overwriting in the code in this source file. Let's compile. Let's launch the code to the submit to the queue. Again, we are using the queue of a GPU, an integrated GPU in the cloud cluster. And as can be seen here, the data are initialized by 0, 1, 2, 3, 4, 5, and here it is multiplied by 2. So what in theory we have to see out is 0, 0 multiplied by 2 is 0, 1 multiplied by 2 is 2, 4. So it's double the elements of the initial array. Well, the use of unified shared memory, you can explicit specify how the copy are done to the device, as can be seen here. So we are creating the data explicitly in the device here. We are copying the data that these data were created in the host. We are copy explicitly to the device like this. And now we are launching the kernels in this part. So this copy needs to be finalized in order to submit this one, because in this one we are using the data device that have been completely done in the previous kernel. So we are write down the dependency, this E1 dependency. It is necessary to complete the dependency of E1 in order to launch the second kernel. And the third kernel, the copy is copy back. So again, it is necessary to finalize this kernel in order to launch the copy back data from the device to the host. So again, it is create the dependency, the E2 dependency. So it is wait until the E2 is finalized. So again, we are going to run the code. So take into account that the data are initialized exactly in the same way. So the vector are created with 1, 0, 2, 3, 4, 5 again. And here in the kernel are doubling the data of each component of the array. So you can see here that unified shared memory, you also can use it as in an explicit way if you like. Well, you can check here. The vector are doubling, each component are double that initialization. Well, so the idea of use the unified shared memory have three strengths. The first one is that it's very useful for porting one C++ code because you not have to change a lot of code lines because the pointer is exactly the same from in the host as exactly the same in the device. It's very easily to port one code. Its functionality is really quickly and is quite near of the peak performance obtained if we are not using the shared memory, the unified shared memory. And also it allows to control the data movement. It is required, for example, in the case of explicit data movement, and as I showed you in the previous example. Well, here you can management the data dependency by means of wait in the queue. In fact, I show you if there are, you have to wait to the execution of one kernel in one queue. You can use it here. You can use also in order queue, that it is also new related to the SYCL standard. And also you can use depend on that I show you in one of the previous examples in order to specify what are the dependencies between one of the kernel launch to the next ones. Well, so here, for example, I'm going to present the same example. For example, here it is initialized data. It is initialized all elements to 10. It is created in a shared memory, unified shared memory. We have three kernels. The first kernel, it is adding 2 elements. The second one it is adding 3, and the third one it is adding 5. The main of the problem is there are some data dependencies, so we cannot launch this kernel until we cannot launch this kernel until the first one it is already compute. And this one is exactly the same. It is cannot be launched because there is data dependency respect to the previous one. Here, as execution in the kernels are in an asynchronous way, we are showing in the screen the data, but you have to wait until the kernel is finalized because it is run the queue in an asynchronous way. So you can put it here, wait, or you can create here a dependency as in this way, and saying that the second kernel have a dependency respect to the first one, and so on, so on. Well, you can check it, the different solution. In fact, there is some of the solution here if you would like to check it, or if you would like to do it later. Well, I'm going to move to another new idea of oneAPI, which differs from the SYCL standard, that are subgroups. Subgroups is another way to present the parallelism in execution of the kernel. So let's see how it is work, and let's see how normally it works, the end range expression of the parallelism in one kernel. So normally, when you create a kernel, you can express the number of instances can be created, and you can do it in one of the dimension, 2 dimension, or 3 dimension. And all of that can be done by means of this empty range. The empty range create a number of instances that are launched in one kernel. Of course, from the point of view of the parallel, of expressing the parallel, you can divide in different level of parallelism. So by means of empty range, you are creating the total amount of instance, but you can subdivide this instance in this part that are called work groups. So here there is a work group. With oneAPI, also you can tune a little more, creating another parallelism level by means of subgroups. So you can subdivide also the work group into subgroups, which is new, as I told you, in oneAPI respect of SYCL. Of course, the vocabulary of empty range are extending of the vocabulary used in CUDA, OpenCL of SYCL, but what is really new in oneAPI is the idea of subgroups. Well, as I told you, when you invoke a kernel, you specify the parallelism by means of empty range. So you express which are the numbers of work items in all the idea. So if I define this concept, the work item represents the individual instance. Normally it is mapped as a thread. So one thread executes one item. Our group is an abstraction level of some work items are grouped and are grouped into our work group. And normally all the work groups are scheduled in the same compute unit. It is very common in NVIDIA GPUs as well as Intel GPUs. And what is totally new in oneAPI is the idea of subgroups. The subgroup is the concept where you divide a subgroup in into subgroups. So a subgroup is really a subset of work items. Work items that are in a subgroup. This is new, and our map. This is new in data parallelism as much. It is new in oneAPI. And why it is necessary to define subgroups? Well, normally, in the case of Intel GPUs, it is interesting because this operation can be mapped directly to the vector hardware available in the GPUs, Intel GPUs. And some of the operations of vector operation can be done directly without going to the memory. So it is very interesting in terms of performance. So this idea, as I mentioned here, it is create the subgroup. Well, the subgroup that is specified, it is new in DPC++, and it is interesting because it can be applied directly this vector operation. If we deep in a hardware in a Intel graphic hardware, can be seen like this. So in this graphic, this is a stream processor, what is called a stream processor. Each watch group it is executing this stream processor. Well, inside there are these executing units, and so group can be executed in a vector way in each in these executing units. This is the idea, and it's mapped to this hardware, to this vector hardware. So some vector operation can be done directly without passing to the memory. So this is the idea of using subgroups. So these subgroups help us some vector operations, a shuffle operation, without going to the memory, as I told you. There is also guaranteed memory consistency in terms of subgroups, and also there are another type of operation in terms of vector operation that can be directly mapped by these subgroups that are collective operation, such reduction or elements of one vector and so on. Here I present you an example. In this example, there is the subgroup. There is a class of subgroups, and with the subgroup you can also get information respect of the impedance of the subgroup, and what of the subgroup are recovering into the workgroup. Here, for example, it is shown. You can obtain the local ID of the subgroup. You can also obtain the range of the subgroup, which how many elements are respect of the subgroup. Here, for example, there are 4 elements in the subgroup because the vector length should be 4. You can also obtain the identifier of the subgroup and also the range of the subgroup. Well, and finally, what are the operations that are supported in terms of productivity, which improve the productivity by using the vector capabilities without going to the memory? Well, here you can I can show you, for example, a reduction operation. In this case, the subgroup, that this is the data that are allocated in the subgroup. We are using this part, and it is using a reduction. All the elements of the vector are reduction by means of plus. So we are adding each element to the other elements, and we are collecting what are the sum of all the elements of the vector. Here you have another example, which are the maximum of the vector, which are the minimum. So as you can see here, some collective operation can be done directly without going to the memory. So it corresponds with one assembler instruction in terms of vector instruction, and can be done in only one execution cycle. Well, so I'm going to present these vector operations in the dev cloud. It corresponds with the number 4 notebook. Okay, let's see. Well, here it is expressed how the execution normally are divided by means of ND range. The parallelism are divided are expressed in the ND range way, and this ND range normally is a hierarchy, a parallelism scheme where you have all the instances that corresponds to the work items, and some of the instances are grouped in a work group, or what are here remarked as orange. And in this case, a subgroup have been added by oneAPI in order to use vector capabilities inside of a execution unit. As here it is so how you can identify the local ID of the subgroup, which are the range of the subgroup, etc., etc. So in this example, for example, I create the queue. The queue, of course, although it is default, normally it is selected the GPU if we are using one node with integrated GPUs. So in this case, we are using the parallel for. We are taking the item subgroup, and here only if the zero, if I like master, we are printing all the information respect of the identifier of the subgroup, what is the size of the subgroup, and so on. So I creating the file, and now I compile the file, I launch the execution to the dev cloud. Again, the queue selected, it's the GPU queue, so we are selecting the device by default the GPU. And in this case, I'm going to show you what are the information respect to the subgroup. So as it is noticed here, the Intel GPU, it is selected, and in this case, the size of our subgroup is 16, and this is the first element of 4, the second element of 4, and so on. So there are 4 elements, 4 subgroups, and in each subgroup there are 4 elements. And here I'm going to show you, for example, shuffle operations. You can create like this shuffle operations. You can move and shuffle one of the data to the other without going to the memory. It is not necessary to repeat this to the global memory. This is one of the main improvements of the subgroup that we can apply. And also you can shuffle in another way by means of 2, by means of 1. Okay, you can check it. In fact, there is here an example of buffle XOR buffle shuffle, so you can check it. And also there are also available some collective operations as reduction of adding all the elements of one vector that I'm going to show you in this example. Let's compile, let's launch, and let's show you. Well, in this case, I initialize with the shared memory. We initialize the data. I'm going to print out the value of data, and now I'm going to launch the kernel, this parallel for kernel, and we are going to reduce the data in each subgroup elements. And finally, when it is reduced here, the value of the data, I'm going to allocate the sum in the first element of the subgroup, like this. Well, so this part corresponds with the initialization. The initialization that it is done here. So the vector is created by 1, 2, 3, 4, 5, etc. It is created 1, 2, 3, 4, 5, etc. And now it is reduction. The reduction will be done here in terms of subgroups. So all these elements, the 16 first elements, are reduced. It is add 1 plus 2 plus 3 plus 4 plus 15 plus 16, and it is reduced in the first component as it is done here. It is done here. It is the sum is allocated in the first position of each subgroup. Again, the second 16 elements are reduced in this part, and so on and so on and so on. So what I like to show you here with the subgroups is that there is another level of parallelism that could be applied, and if your code has an operation in can be expressed directly by vector operations such as shuffling or such as collective operation, it is more convenient to do by means of subgroups scheme instead of using in a classic way, because it will be involve some data transferring to the main memory, which reduce the performance significantly. With that I think I finished the first block of the session today. So the session today, as I noticed, will have two main blocks. The first one was the use of Hpc++ and the some of the improvements that it was implemented respect to the SYCL standard. As I mentioned, was basically the use of unified shared memory and the use of subgroups as another level of parallelism that is available in a GPU, Intel GPU. And I would like to finalize this block, this session with another block that is the block that I titled Hpc Tools. In this block, what I would like to show you here is how you can use performance tools that are available in the Hpc toolkit in order to check if your code have some bottlenecks or not, and how you can try to remove these bottlenecks. Of course, identify and also try to solve them. And what are some of the tools available in the oneAPI toolkit, and how you can use it in order to improve the performance of your code. So in this second block, I will show you a Roofline model and how your application with this Roofline model you can have an overview of the performance of your application in terms of function of the main loops, and what are the performance of each loop, and how far you are to the limits of the hardware. If your application is very intensive in memory, or maybe it's intensive in compute, how far it is from the limits of the hardware, and it is so far how you can search for some improvements. Apart from the Roofline model, I also Advisor, which is the tool, one of the tool available in oneAPI, which show you it is convenient to move some of your code to the GPU, because will obtain better performance or not. So as I'm going to show you here in the Intel Advisor, it is convenient to move some of the some parts, and also it is given some numbers of what are the speed up expected if you are using one device at GPU. Also, I'm going to show you the vTune. The vTune is one of tune that was available in the Parallel Studio many years ago in the Parallel Studio suite, and also how you can use it here, not only in CPU but also in GPU devices. And finally, I'm going to show you how you can use an optimized library. Which is one of the key points of oneAPI. Remember that in oneAPI there is one way to use oneAPI by means of the parallel C++ compiler. If you would like to write down all your code and how to develop your code in different type of devices, so how you can develop your code in a heterogeneous way. But of course there is another way, and that I encourage you to consider if your code can use some optimized libraries in order to not porting your code directly high tune code and also evaluating by means of the tools. And I encourage you to use some optimized library as soon as it's possible in your code, because normally you will have better performance as you are doing by yourself. This is one of the jobs that some staff of Intel have been done since the last years, and normally these libraries are really improved in terms of performance, and also it's totally portable to the different devices as CPU, GPU, or FPGA. So I encourage you to use these libraries. It is convenient in your code. Well, what we are going to see in this block is, first of all, a couple of tools, performance tools, the Intel Advisor and Intel VTune. Intel Advisor is not a new tool of Intel. In fact, as I told you, was available in the Parallel Studio suite in previous years. But what is really new actually is that there is another tool with this offloaded advisor. This offloaded advisor have the particularity of can identify the impact and also to show you if there are opportunities of downloading some of the code to a GPU, for example. So this is a really interesting tool in order to check if your application is potential to be offload to the GPU, for example, and give you an important speed up respect of executing in a CPU. Also detects the bottlenecks and gives you a boundary factor of what will be the improvements if you try to solve these bottlenecks. And this is relatively new in Intel Advisor. Of course, the Roofline analysis is also available in Intel Advisor. That was one of the characteristics of the Intel Advisor in previous tools such as Intel Parallel Studio. And also I'm going to show you how, by means of this Roofline analysis, you can determine how far you are of the peak performance of your application, or how far is your application from the peak hardware in terms of floating points operation and so on. And also gives you as new a graph analyzer to visualize with recommendation which of the function or main loops would be available to offload to the GPU instead of executing in a CPU. This is respect the Intel Advisor. Respect the VTune, what is new is actually it is new in Intel VTune that also you can tune how will be the performance of your application in an offloading. So you can check how will be the activity in a GPU as well as a CPU in terms of threads, how many threads are executing in a GPU, how will be the activity, if there are threads who are waiting for another one in a barrier operation, for example, some synchronization phase. And what is also new is to evaluate the hot spots in a GPU. So if this tool analyzes the most time-consuming GPU kernels. Here it's GPU, and also gives you a performance of each source line. So at source line level, you can check how many cycles are involved each operation and assembler level. So you can decide if there is a bottleneck at this level, at source line level. So it goes really in a deeply way of your application. So more or less, I present here how will be the flow of using these tools. So maybe you can create a new code and you are using the data parallel C++, or maybe you are using an existing C++ code that you previously developed, and maybe you are using OpenMP, whatever. So in this case, or maybe you are coming from one CUDA code and you are using one DP C++ compatibility tool that I showed you in the last session, I think on Friday. Well, okay, So coming from all this short code, the Intel Advisor will show you if it is disabled or if it is you can take it into account to offload some part of your code to an accelerator. So it gives you an advice if your code is more interesting to running in a GPU instead of using the CPU. Well, and finally, the Intel VTune, you can check if your code have some hotspots. There are some bottlenecks and at runtime, and you can try to optimize the code focusing where the bottlenecks appear. So this is more or less what I'm going to show you in this block of slides. So we are basically talk about today in this blog about Intel VTune, and also we are going to talk about the Intel Advisor. And both of tools, these performance and analysis tools, are available in the base toolkit. So you can directly from porting your code in VP, C++, or coming one code who have been developing CUDA and using the compatibility tool to evaluate with these tools how far you are of the limits of your hardware, and it is recommendable to use a GPU instead of the CPU to run your code faster. Well, let's start with the Intel Advisor. Well, the Intel Advisor allows you to give different type of analysis. Some of the analysis was previously available in the Intel Advisor in the version of the last year. So the vectorization, the vectorization, optimization in terms of vectorization, and also Intel prototyping and so on was previously available in Intel Advisor. I was not talking about during today of these tools, but I only would like to tell you that of course these analysis still are available in Intel Advisor. What I'm going to focus today is in the Roofline, analysis. That is true that Roofline analysis was previously available in the Intel Advisor, but there are some features new in the Roofline analysis that I would like to comment and deepen. And also, the other thing that I would like to talk about today is how, by means of Intel Advisor, I'm giving you some advices of your code, or part of your code is interested to offloading to the accelerator. So I will going to focus in Roofline analysis, and I'm going to focus in build heterogeneous algorithms in the Intel Advisor tool. Well, so as I told you before, Intel Advisor is a set of tools you can analyze. You can use the Intel Advisor to analyze many things. You can use the vectorization. That is not the key point today. You can use the Roofline that I will deep on. I'm going to focus in the Roofline analysis today, and give you the Roofline analysis because by means of a single shot, you will have an idea which are the performance of the application and how far you are of the hardware ceiling, or how far you are of the limits of your hardware. So I'm going to show you how, by means of the Roofline analysis, you can decide to focus and to put more effort in times of coding in what are the routines are more far from these ceilings. Of course, in Intel Advisor is still the threading advisor. That is true. And the other thing that I would like to focus is the flow graph analyzer. It is based on Intel TBB and give you an idea of which are the more recommendable, the more interesting routines to be offloading to the GPU. Well, so let's introduce the Roofline analysis. The Roofline analysis and what is exactly new in the Intel Advisor 2020, which it came with the first oneAPI version. Well, the roof analysis as the previous roof analysis, visualize the arithmetic intensity of a loop or a function against the footprint of the memory access. This is the idea. And with this visualization, gives you how far you are of the limits. If your application is more intensity in terms of memory access, so your bottleneck is in the memory access, or because your bottleneck is because it's a compute application and the bottleneck refers to that it is needed more computational capabilities. So what is really new is the previous Roofline was only focusing data in the RAM, in the main memory, and actually it is giving you more detailed information about what are the transactions between all the different cache levels. Not only focus in the RAM, but also for the cache memory levels. So this is new in the Intel Advisor 2020, and also gives you some optimization steps that and also some suggestions that what was done previously as well in the previous Intel Advisor. Well, so what also it is new in the Advisor 2020 is that by a single shot, it gives you an idea if there are some different routines, for example, here the multipliers routines, that it's interesting to thinking to move to an accelerator or not. In this case, for example, it is said that the times involved in a CPU is like this blue bar, and it is executing a GPU is the green bar. So you can obtain a speed up of 4.4 in terms of speed up if you are using the GPU instead of using the CPU. So what is new in the Intel Advisor is giving you some suggestions of which routines is interesting to move to the GPU. Well, and what are the candidates, the good candidates to be offloaded, as I mentioned before. In this case, for example, speed up is close to 9. So give you a detailed information of your application and if it's profitable or not to offloading the code to the GPU. And also it is given in this part, it is given some information related to the access to the main memory. If the most of the access are done in the first cache or the second cache or the third cache, that's all. Well, let's talk about a little more about the Roofline model. Well, the Roofline model, it is not new. It came from Berkeley. It has at least 10 years or even 15 years as the first paper was published. And what this tries to show you is the equation of your application. What are the limits? What are the limits? If the limits are related with the performance or if the limits are limited by the memory access. So here are the two limits that normally it is presented, the bandwidth to the main memory, and if the limit of the peak of the measure in flops or in gigaflops. So what I would like to check is what are the limits and how far my application are of both of these limits. So normally, if we have a code and in the code we are going to check what is the arithmetic intensity. The arithmetic intensity, it is seen as the ratio between the operation in floating points with the cost of accesses to the main memory measured in bytes. So in this example, for example, in this example that it is shown here, I would like to do this operation. There are two floating operations, the adding operation and the multiply operation. So there are two floating point operations, but it is necessary to access to the B, to the C, and to the D in a read way and also store the result in the A. So there are 4 access to the main memory, 1 respect to the write and 3 reading. So if the data corresponds with 1 floating point, a single floating point of 4 bytes, in total we are accessing to the main memory to 16 bytes. So arithmetic intensity is the quotient, the ratio between these 2 operations between the 16 bytes that are needed to complete this operation. And with this arithmetic intensity, we are going to see if our application is memory bound or is a compute bound. This is the idea of the roofline. So in this graph, we are creating in this graph 2 lines. This line corresponds with the memory access. The memory access, that is the peak of the bandwidth peak of this platform. And this peak corresponds with 119 gigaflops by seconds. And the other line is this one corresponds with the peak of floating points operation that are available in our architecture. That in this case is at least 1,000 gigaflops. So depending if our application is here or is there, our application is more memory bound or is more compute bound. This is what the rule line is trying to show you in a single shot. So for example, your application with this arithmetic intensity came here. It is said that you are so far from the limit that will be here. So you can apply another different level of parallelism, such vectorization or threading, and you can move from this point to the upper point. And also you can move in this line if you optimize the memory access. So if you optimize to memory access, maybe you can move to the right point. And instead of being here, that is memory bound application, you can move to a compute bound application. So let's see the memory level of roofline. Well, the idea of the roofline is to present in a single shot how far you are of the limits. It can be seen here in the left part of the slide. So there is the peak of the bandwidth, there is peak of the floating point operation. So you have one of your application that the point is here. You can consider to apply some optimization in order to increase the performance. It is said that okay, this application have a big gap respect to the peak, so can be improved a lot. So please take some effort in terms of coding effort and try to improve your application. So this is the idea. This is not well optimized if it is in the red part. So please try to check what is the bottleneck and try to improve it. So if it is in the grid area, it is said that okay, it is well optimized. It is the utilization of the platform is really good. So maybe you can consider to optimize a little bit, at least if you can move to more to the compute bound that is related here, the compute bound, or it is memory bound. Please move to the right in order to be compute bound, and you have more margin to improvements. Well, as I told you here, if your application is in the left part, it is memory bound. So please try to invest in improve the memory hierarchy with some techniques like blocking or so on, or try to find out what are exactly the problem of your application. And if your application it is in this part, you have a lot of margin to improve your application. So try to invest your time in expressing your application in terms of exploiting data parallelism by means of vectors capabilities or even with threading, and try to move. So with this idea, you will have with the roofline, you will have an idea of how far you are to the limits. If you are doing well in your application, if you can express, you have developed an application that exploit the hardware capabilities properly or not, how far you are. And if you are and you have margin of improvements, please invest your time in memory, exploiting the memory hierarchy, or trying to express parallelism and trying to improve the performance, the peak performance. Well, this is more or less the idea of the catch-aware roofline. How far you are of the limits, where you have to put all your effort. Well, so Intel Advisor adds support in this catch-aware roofline, and it is supporting by reruns and analysis on your code. Of course, this analysis will take you a little time because your application have to be run several times. And the idea of Intel Advisor is it is giving you some recommendations on where the bottlenecks could be appear, and how can you apply some solutions that can be success or have been that obtain a really success performance in terms of execution times or floating points operation. To obtain the roofline model, it is necessary to pass approach to two executions. The first one corresponds with a survey that normally it is called a general survey, and the second one which is focused in the floating point operations, and it is collecting the floating point operations in terms of the arithmetic intensity, if it is using or not the vector capabilities, and so on. And normally the overhead it takes one time the execution of your code to obtaining the first step, and between three or 5 times the execution of your code to obtain the floating point traceability. So the Intel Advisor have the particularity of you can export your roofline to a HTML file, and with one file that is a little bit interactive, so you can try to check what are the bottlenecks and how will be the behavior of your code if you modify some parameters related with the catch, the size of the catch, of the bandwidth with the catch, and so on. So it can give you a projection of what will be your application in another type of architecture, or if it is advisable to move to another architecture with more capabilities or not. So let's see how it is working in a GPU, the Roofline model, and how you can obtain. Well, the Roofline model, as I noticed, was available in Advisor in the previous Intel Advisor versions, but the model that was available was what it is known as catch-aware Roofline model. It is based on instrumentalization, and as I told you, it is necessary to execute 2 times, one for sampling and another to checking what are the overheads and the instrumentalization of your code. And as the main what is in favor is it is easily to characterize your algorithm. However, sometimes it's not very easy to interpret, depending on the point, how far you are to the limits of the hardware. At least if your application is memory bound, because the idea was only with the DRAM. What is really new in the Intel Advisor 2020 is this new model. This new model, which is based on the memory level roofline, so it is apply the same idea as in the catch-aware roofline model, but using a simulator or the behavior of the catch. So it is evaluate the traffic between the different level of the cache, the L1, the L2, the cache that is shared with a multi-core and also with the access to the DRAM, and you can obtain more closer the original Roofline model and give you a more detailed information about the improvements that can be applied in your code in order to improve your code. The main drag box of this new model is it requires more time to be run. The execution or the overhead of the execution is more intensity. So the result that you will obtain using the Roofline will take more time. So it is more or less the figure that you can obtain nowadays with a new model of Roofline. Instead of having only one point, you will have different type of points, and you can see how far you are to the different level of the cache. So in this case, for example, the blue point, it gives you that you have a lot of margin in order to find the limit of the L1 cache. Also, there are different points corresponding with the different levels of the cache, and the last one that corresponds with the DRAM. That is actually the point that showed you, or was the point that was showed you in the Intel Advisor in the previous versions. So it gives you a projection with the using the different level of the cache, and it is done because there is a simulation about the traffics between the different level of the hierarchy memory. If we are going, or if we focus in the architecture point of view, the GPU, we have all the executed units divided by this sub-slice, and it is connected by the first level cache, and all are connected with another level, memory level that is the shared memory, and normally it is called L3, that is shared between all the execution unit of the GPU, and also there is another level that corresponds with the SLM, the memory access to the shared with the CPUs, and finally with the RAM. So also this model, the model respect to the GPU, is also available in the Intel Advisor. This is the idea. The idea is to collect more or less what are the traffic between the different level of the cache line. So instead of having only one point, one dot, you are going now to have four dots corresponding to the possible improvements of your model, your application using only L1 or L2, L3, DRAM, etc. So one of the main drawbacks that I would like to notice here is this analysis. It's only available if your code have a unique stride. So if your data are all of them consecutive in memory. If there is another stride, this analysis is giving you information that is not correct. So instead of having one dot, here you have your all dots. One corresponds to L1, L2, L3, and DRAM, and you can check how far you are all the limits respect to the DRAM, the L3, the L2, or the L1. And if it is taken into account, if you can apply another parallelism levels, such vectorization or so on. Also gives you some metrics respect to the percentage of the access to the different levels of the cache, and what is the amount of the memory which are accessible in each of the levels. So it gives you an idea. Most of the references are done here into the L1, so in theory, this application is relatively well developed in terms of memory exploitation. So maybe you can think in applying another type of parallelism levels in order to improve the performance. So as a summary, as I told you, the roofline gives you an idea, of what are the bottlenecks, or in CPU or in GPU. It is totally visible, and also have the possibility of supporting the HTML file, and you can check how will be the behavior of your application if you modify some of the parameters respect to the GPU. Well, how you can obtain the roofline? You can do it like this. You are executing the advisor, like here. You can use a collect roofline. In this case, you are enable the cache simulation, so you are using the novelty of the Intel advisor. And here will be your executable with the parameters of the executable. Of course, it involves the collection of the roofline and the second run that takes the information respect to the floating point operations. And once the trace is collected, you can visualize by means of the GUI with this advisor GUI. And all the trace that was collected here in your directory, in your project directory, is created the HTML file. So that is the idea of our collection. So if you are using, for example, this in a CPU, you can do it exactly the same. And if you are doing in a GPU, it is necessary to add this profile GPU flag. Okay, but most of them it's exactly the same. Both of the collection of the samples and finally the visualization by means of the key. And this is more or less one of the execution that I'm going to show you again. Well, another of the particularity that the Intel Advisor have is the GPU offloading. As I told you, it gives you an idea of if it is interesting or not to offload some codes, and how will be the speed up of using GPU instead of CPU. So this is interesting of thinking in move some part of the code to the GPU, and you will have directly transparent a big important improvements. So the way in order to use the Intel advisor and also the cache-aware roofline analysis is, first of all, check how far you are this dot from the limits. Later, if it is focused, you have to focus in developing a more memory exploitation or more compute exploitation, and also what are the best candidates for optimization, taking into account if your application is more memory bound or compute bound. So this is more or less the flow of using the Intel Advisor. So I'm going to show you a little bit with the Jupyter Notebook how you can use the Intel Advisor in the Intel Cloud. So let's see. I don't know if I have enough time to run any demo, but I'm going to show you a little bit what you can find. Well, I'm going to show you the Intel Advisor. Here you have Intel Advisor. I select as an example matrix multiply. So you can download from this GitHub source code. You can download the sample for matrix multiplication. So here there are the lines. You can init the GitHub, and you can download only the sample corresponding to the matrix multiplication. here it shows you more or less the code. There are different versions of the multiplication of the matrix. There is multiply 1, multiply 1, 1, so on. But what I would like to show you here is how you can use the Intel Advisor. So first of all, you have to compile your code. Once you have downloaded the code, you have to compile the code by means of the Data Parallel C++ compiler. You can submit the execution, and it is giving you the time of the execution. For example, here it is giving you that the execution was done in 1.89 seconds, and how you can use the Intel Advisor, how you can use for obtaining the roofline. Well, I create here one script in order to collect, as I mentioned in the slides. It is necessary to do 2 runs, one to collect a survey and the other to collect the floating points. It is necessary to enable the GPU profiling like this, and now it is creating in this file the HTML file. Well, if you run, it will take a lot of time, at least 3 minutes or 4 minutes. So I think we don't have enough time to show you, but you can try to replicate the Jupyter notebook. Finally, as I would like to show you this part that corresponds, if it is so, yes, it corresponds with the HTML file that was created here. So this, oh, sorry. Okay. This corresponds with the Intel, I don't know. It's not working properly. Let's see if I'm going to Advisor here, Roofline Model. I'm going to download it and open locally because I think it's better. Okay, let's open it here. Okay, it is better. Well, this corresponds with the matrix multiplication. In fact, it is seen here that it corresponds with the version matrix 1. So this is in the Intel Advisor Roofline Model. As I can check here, if I click double click, and it is open, and as you can see, for example, how will be the performance and how far we are to the GTI memory. So it is in this point, but you can go up, and it is shown here. It is possible to have a speed up of at least 4 gigaflops, a speed up of in times of 4 times if we improve it. You can also check here how will be the behavior respect the sorry, let's click again. Okay, if we are using L3 instead of DRAM and so on, so you can check that you have margin to increase the performance in at least 4 times if you implement better your matrix multiply. Well, this is what I would like to show you here in the Jupyter. Well, I show you how you can obtain the Roofline model. Also, I would like to show you which routines are interesting of loading. The idea of using the Intel Advisor is you measure all the execution in CPU. It is important to do that, because if you are selecting by default the GPU queue, normally if it is not done the selection of the device manually, normally select the GPU instead of the CPU. So it is necessary to change a little bit the code and select the CPU. So once the CPU is selected and is executed, it gives you a measure, an estimate what was the performance obtained if you offload some part of the code in a GPU. So this is the idea that we have. So for example, here it is said that it's not profitable to offload this part, but maybe there is another part that yes, it is profitable to download. So the flow is to compile the code with the -G and O2, obtain a survey, and in the instrumentalization of your code, and it gives you the idea of what is better. So what I have done here is to collect again the data, and here it is observed that, for example, if matrix 1 it is run in a GPU, we will have an expected speed up of at least 5.8 times better than executing in a CPU. Of course, if we click here, it refers with the source line that are here. That is the function that I created for the multiplication of the matrix that are here. You can check it. That are. I'm sorry because I don't know why it is not so easy to show you, but you can show the source line codes of this part. Also, you can click in call tree and it gives you this tree of what are the functions running in the CPU and what functions are potential to run in a GPU and will be accelerated. Okay. Well, so let's talk about a little bit about the VTune. The VTune also allows us to give an analysis respect to performance observed in a GPU, and there is new that there are actually two analyses that are available: GPU offload and GPU compute hotspots. So these two analyses are new, and you can profile your GPU. The first one identify what workload are done in a CPU or in a GPU, and if what is the performance obtained and the activity of the GPU or the CPU. And the second one identify the limits observed in terms of performance. So it's also available in a GPU, and it's given an instruction level how much time involves the execution of each instruction. So you can identify kernels which are inefficient, and in a kernel, what parts of the kernel are inefficient in terms of times that involve one instruction, and also in terms of memory access. Well, how you can do it, the profiler, by means of VTune. Sorry, I don't know why it is moved. How you can do it? Well, you can do it applying these flags. Okay, you have to add these flags in compiling phase to be enable the profiling. And as can be seen here, for example, can be seen how will be the execution in a GPU, how many threads are creating, and if the threads in the GPU are totally idle or are executing currently, if there are one thread who are waiting due to one synchronization phase or whatever. And the second analysis that you can do it is the offload analysis. The offload analysis is giving you some ideas that I try to highlight here. What are the function or who involve more time? So check it here. Who are the function who involve more time? So you can try to check how will be the utilization. In this case, the utilization of the GPU is not so good because it's only 4%, but I'll give you an idea of if it is interesting or not. In fact, also you can obtain how will be the memory footprint in terms of access. If some part of the instruction are stalled due to memory access and so on. And here it is giving you an idea of the execution units, if they are active, are idle, or are stale, as can be seen here. So this is more or less the idea of the profiler. You can click on one of the points of the graph and it gives you exactly the line of the code who are executing in this moment. So it's really very fine-tuned, can be applied. So the instruction level, for example, it's shown here. In this case, the scene and cosine routine involve time due to the control flow, and most of the time are executing floating point operation and so on. To give you the idea of which are the utilization of the vector capabilities of the GPU. Well, I show you here more information, links to more information, because I have not so much time today for talking about this, but respect to MPI, the compiler, the advisor, what is interesting, I was moving on the advisor today, and how you can execute the profiler by means of the VTune. Respect to the collection of the data of GPU, you can execute both of these profilers, the profilers of loading, that give you an idea of how much time are executing the routines in the GPU, or what are the hotspots in terms of memory footprints and instruction footprints and so on, respect to the second analysis. Okay, there is another Jupyter notebook that is presented here. Most of the analysis that is available in the Jupyter is what I was commented in the previous slides. And I would like to finalize by the use of another tool, that is the use of one optimized library in the oneAPI. So oneAPI, in this case, I'm using the oneMQL, that is a well-known library for mathematics operation. It is include the classical basic linear algebra subprograms, operation with vectors, with matrix vector, and so on. Even it is include some operation like BLAST with a spare matrix, LAPA, generation of random numbers, some statics operation, and so on, even Fourier transform functions. What I would like to show you here is how will be the execution of this matrix multiplication by means of oneMQL. And I show you here a new routine that I created routine. This is multiply MQL, and I create 3 buffers for the matrix A, B, and C, and how can be invoked. So the blood routine is GIM, that is very well known, and is a classical matrix multiplication, and it is applied here buffer A, buffer B, and buffer C in order to take into account the input data, and it is completely executed here. Of course, you have to modify the source code. So here I add this new function to the multiply.cpp file, and also I added the line respect to the headers. And now I selecting with this macro that the function we are using is what I create now, the multiply with MQL. Again, there are the lines to compile the code. We execute the code. This is the execution. And what I would like to propose you is you can use this again. You can use the Intel Advisor library. You can use the VTune library, the VTune tools, in order to check how far you are to the limits of the hardware capabilities. And also, I would like to show you. I would like to propose you that if you change the size of the matrix, you can obtain an important speed up if you are using the GPU. So if you increase the size of the matrix to 8,100 and so on, I observed an important speed up in terms of 3 or 4 using a GPU instead of CPU. And of course, the using of this library it involves an important reduction in time execution respect to the version that was done. This multiply one version or the other version. So I encourage you to try to replicate the notebook the notebook samples and trying to check how will be the performance observed when I'm using a specialized library that in theory not. It is optimized not only for CPU but also for GPU or even FPGAs. And that's all. I don't know if there are some questions. Let's check it.